Good morning, good evening, good afternoon, depending where you are. We welcome to the IEEE Geoscience Remote Sensing Society Young Professionals and ISPRS Student Consortium Summer School 2020. It is an event promoted by the Geoscience Remote Sensing Brazilian chapter together with the Chilean Geoscience Remote Sensing Society chapter. Well, before we start, I just want to add a short video of one of our sponsors, the ISPRS Student Consortium.
Hi everyone, my name is Cheryl Rose Reyes, and I currently serve as the president of the International Society for Photogrammetry and Remote Sensing Student Consortium. I am very happy to welcome you all to the 6th edition of the IEEE GRSS Young Professionals and ISPRS Student Consortium Summer School this year. To start this event, I would like to present a bit about the ISPRS Student Consortium. We are the official representation of the youth to ISPRS. We link students, young researchers, and professionals worldwide interested in photogrammetry, remote sensing, and spatial information science to promote their scientific and professional developments. We advocate imaging and geospatial science for informed, scientifically valid, and technologically sound observations of Earth conditions and trends that lead to improved and effective decision making. The consortium is also accepting registrations for individual membership. Please scan the QR code in this slide if you are interested to join us. I work together with members of the board of directors from all across the globe. Charles from Uganda is our vice president. Charmaine, who is currently in Ireland, is in charge of our newsletter. Mustafa, our social media administrator, is from Turkey. And finally, Sona from Azerbaijan is our web administrator. One of the major events that we host and coordinate every year are the summer schools. In 2019, the summer schools were in Uganda, Poland, South Korea, and Brazil. These summer schools provide international learning opportunities for students and young professionals at a minimum cost. This year, we scheduled 3 summer schools, but due to the COVID-19 situation, 2 of them were postponed, and we are sincerely thankful to the organizers of this summer school for making this an incredible virtual event. This is the first ISPRS Student Consortium Summer School that will be hosted online, and as you can see, we have an amazing lineup of speakers who will deliver lectures on remote sensing and machine learning. The consortium currently hosts the virtual rooms and the webinar series to provide our community with more opportunities to learn and interact with experts in our scientific community. The webinar series was conceptualized in 2018, and we have organized webinars on Google Earth Engine, computer vision, and machine learning. The virtual rooms is an initiative to keep the members of the consortium connected during this challenging time and to help them navigate our changing lifestyles. All the resources for the webinar series and the virtual rooms are available on our website and our YouTube channel. We also publish an official newsletter called Spectrum, which covers the broad applications of remote sensing, photogrammetry, and spatial information science, and welcomes contributors from diverse backgrounds and disciplines. We publish 4 issues a year, and our most recent issue is related to the current pandemic and the significance of geospatial information in tackling the impacts of this global health crisis to our society. The ISPRS Congress is one of the biggest gatherings in our scientific community, which is held every 4 years. The Congress hosted a virtual event for all papers submitted this year and postponed the in-person meeting for 2021. During the Congress, the consortium will be hosting a 3-day youth forum, which will feature the following activities: speed dating, technical sessions, a special session on women in remote sensing, photogrammetry, and spatial information science, a panel discussion, the General Assembly for our members, a student night, another summer school, and will co-organize a mapping party. The consortium would also like to invite you to nominate papers for the Excellence Award to be given during this event. Please scan the QR code for eligibility and nominations. Also, please visit the ISPRS Congress official website for updates. Finally, I would like to invite you all to join our communities on Facebook, Twitter, and to visit our website for all the information shared in this presentation. And again, I would like to invite you all to register as an individual member by scanning the QR code on the right. This is the end of my presentation, and I wish you all a meaningful summer school. Thank you very much.
This was a recording of Cheryl Rose Rines from the ISPRS Student Consortium, welcoming you all for this event. I have also another short video, I promise, from Paulo Gamba, that is currently the president of the Geoscience Remote Sensing Society.
Good morning, my name is Paulo Gamba and I am the president for the year 2020 of the Geoscience Remote Sensing Society. Okay, so first of all, what is a scientific society? What is GRSS? So a scientific society is a group of scientists, researchers and practitioners with common interest and common framework for building a community. In our specific case, we are people who are dealing with theory, concept and techniques of science and engineering as they apply to remote sensing of the Earth, ocean, atmosphere and space, as well as the processing, interpretation and dissemination of this information. So what are the activities of the IEEE Geoscience Remote Sensing Society? Well, we have a number of applications. We support conferences. We have professional activities. We have a number of information service and technical activities and education activities as well. We are a global community, which means that we are arranged around a large number of groups of people that we call chapters all around the world. We have currently more than 90 chapters all around the world. As a result, GRSS disseminates premium science by means of its three main journals, which are the Transactional Geoscience Remote Sensing, the Geoscience Remote Sensing Letters, the IEEE Journal of Selected Topics in Applied Earth Observation and Remote Sensing, but we have also a magazine, which, by the way, has a very, very important role. We also provide opportunities for the different communities, like, for instance, the community working on image analysis and data fusion. We also sponsor community-driven events, like the very successful Earth Vision workshop, but also the SpaceNet Challenge data challenges here, which is organized by SpaceNet. We support also community-developed tools like the DESE website, which is Data and Algorithm Standard Evaluation website, and also activities related to RFI observations. So we also facilitate and connect. We have a number of activities at in our main conference. We have the so-called TIE events, but we also organize different events related to connection with companies, industries. We have a number of activities like for young professionals, for women in engineering and in geoscience and remote sensing. And we share our knowledge on hot topics by means of distinguished lecturers and industry speakers. We have also a number of educational activities. This is one of them. This is basically, let's say, one of the many different small educational videos for kids that we have in different languages, but we have also, in addition to that, a number of webinars, which are also for people who are not kids, about remote sensing in different languages as well. We offer continuing education by means of webinars, which is especially important and useful in this situation where we are not able anymore to move around the world as we were in the past. So we can support continuing education of students and young professionals through conferences, journals, our magazine, webinars, and so on. We can promote capabilities of the different communities, algorithms, dataset, by means of the data fusion context, by means of dedicated events at our conferences, by means of the industrial distinguished lecture or industrial speakers. We help connect companies and young motivated people by means of the young professional event, by means of student grants, by means of the TIE forum. And we make the different community of Earth observation practitioner and researcher be aware of their and your topics of interest. So GRSS is actually a community of communities where we could together share and promote ideas, systems, and dataset. We can meet with other communities and gain from their perspective, and we can build different collaboration to learn more from each other's and to come together in conferences. Thank you very much, and I hope you will enjoy this summer school and all the interesting topics and talks that you are going to listen during these days.
This was another interesting welcoming talk from Paulo Gamba, the current president of the Geoscience and Remote Sensing Society. Well, now I would like to call Fátima Sombra de Medeiros. She is professor at the Federal University of Ceará, UFC, and she recently became also a senior member of the Geoscience and Remote Sensing Society. Fátima, it's with great pleasure that we receive you here. I will give the room for you so that you can introduce the other shares of these sessions and also our distinguished lecture.
Thank you, Geraldo, for introducing me. Good morning, good afternoon, good evening to everyone who is attending this meeting. And I welcome your attendance at this meeting, which is part of the 6th Young Professionals and Students Consortium Summer School 2002, which is supported, as Geraldo said, by IEEE GRSS and ISPRS societies. I would like to introduce you our invited researcher, Professor Carlos Cárdenas from Chile, and from Universidad de Magallanes, and Aline Marra from Brazil, Unesp, who will be joined in this section to coordinate it. And we thank our distinguished lecturer, Dr. Carlos López-Martínez, for accepting the invitation to present us the lecture entitled Basics of SAR Polarimetry from Universitat Politècnica de Catalunya, Spain. And I will present you a short biography of our invited speaker. Dr. Carlos Martínez received the Master of Science degree in Electrical Engineering and his PhD degree from the Universitat Politècnica de Catalunya, Barcelona, Spain, in 1999 and 2003, respectively. He is an associate professor in the area of the remote sensing and microwave technology in the Universitat Politècnica de Catalunya, Barcelona. And his main research interests include synthetic aperture radar SAR theory, statistics and applications, multidimensional SAR, radar polarimetry, which is the theme of our lecture, physical parameter inversion, advanced digital signal process, estimation theory, and harmonic analysis. It's a pleasure to have you in this meeting, Professor Carlos, and the room is yours now. Thank you.
Thank you very much for this really kind introduction. First of all, I would like to thank the organization for this really nice invitation to to present here the basics of SAR polarimetry. So I'm going to share my my screen so you could see. I hope you see. Do you see my presentation now? Yeah, perfect.
Yes. Yes.
Okay, so as Fatima kindly introduced before, I will present in the next 15 minutes what for me are the basics of SAR polarimetry. Here I wanted just to give you all my contact information, so in case you can or you would like to have more information or to put me questions, you can contact me by email or by LinkedIn. I'll be glad to answer your questions. So let's go to start. Which are going to be the objective of this lecture? What we will reach at the end of these 15 minutes. I hope that I will present you the principles of polarimetric synthetic aperture radar for Earth observation. So you will know which are the principles behind this kind of diversity for SAR data. The second point I would like to highlight in this presentation is to give you the information about which is the main physical information content behind the polarimetric data, what type of information you can retrieve from polarimetry, from polarimetric radar, basically. And at the end, I will close my presentation with some applications, not all, but with the main application. Basically, I will present applications on classification and change detection, which are really a hot topic nowadays. So in order to reach those goals, I will go through this classical outline. The introduction, I need to explain first where is the origin or which is the origin of polarimetry. So that's why I introduced wave polarimetry. Then how we use polarimetry with radar, scattering polarimetry, and then finish my presentation with a set of applications. Okay, so let's go, first of all, with a brief introduction, just to settle the framework of this presentation. I expect, or I can imagine that most of you know about a synthetic aperture radar, the classical synthetic aperture radar where you obtain one image, but the most important thing of radar is that you can have multidimensional approaches. Basically, you take images of the same area under some kind of diversity. For instance, in the case of a spatial diversity, SAR interferometry, you are sensitive to the topography. If you increase even more the number of channels, you can create differential SAR interferometry where you are sensitive to the changes of topography. And if you play with the wave polarimetry, and this is the objective of this lecture, you can be sensitive to the geometric properties of the target and also, in some times, to the dielectric constant, so therefore sensitive to the water content. You can even increase more the number of images. You can mix polarimetry with interferometry. You can go through polarimetric SAR interferometry to SAR tomography or multi-baseline interferometry, multitemporal SAR, and at the end, I will present you a combination of polarimetry and multitemporal SAR, or you can combine polarimetry with multi-frequency to have different characterization of the targets. But the objective today is what I have highlighted in here, to present the basics of SAR polarimetry. So, polarimetry, like any kind of multidimensional SAR images, consists on the acquisition of different images of the same area. In the case of polarimetry, our diversity, the thing that changes between every image is the polarization of the transmitted or the received waves. And this is what I have shown here on the top. You have three examples of images acquired between HH, HV, or BB, but refers to the polarization in transmission and reception. But the richness of SAR polarimetry and the richness of any kind of multidimensional SAR image is not the fact that you are acquiring the SAR images or different SAR images, but the fact that they are correlated, as I indicate here. So basically, the images keep some relation between them, and we can exploit this relation to obtain more information than the one obtained with the simple SAR images. And this is what I show here. For instance, on the top of the color images, you can see the correlation between the HH and BB, or the correlation between the HH and the HV, and you can see that you have two parameters, amplitude and phase, and both of them show the data of the area being imaged by the system. So let's go to the origin. What is wave polarimetry? What is polarimetry at the end, okay? So when you play with electromagnetic fields, you need to go through the Maxwell equations that basically control the generation and the propagation of the electromagnetic wave, and also the interaction, and this is important, of this wave with the matter. And this is where our interest is, and we will see later on. So basically, if you solve the Maxwell equations in the free space, what you get, the solution, is an electric field, okay? And the electric field, as indicated in here, okay, depends on space and time. Which is the shape, which is the form, the mathematical form of this electric field? So it corresponds in its most basic form to this expression. You have no component of the propagation direction, that in this case we consider the Z direction, okay? Our field is propagating in the Z direction, but we have component in X and Y. And you can see here the shapes. Both of them are cosines. So basically, our field E is this red arrow I representing here. And the composition into the two components are the blue that corresponds to the X and the white that corresponds to the green. Okay, so basically, if we analyze the evolution of this field in space and time, it describes a kind of helix. But what happens if we cut the propagation direction transversally, and we plot the shape of the form that is described by the tip of the electromagnetic field? If you make that, and you can make that with any kind of software at home. I did this results with MATLAB, for instance. Just to put an example. If you look at the shape here describes an ellipse, which is in this case is the most general case, I would say. Polarimetry, polarization ellipse, is nothing more than the shape of the figure described by the tip of the electric field. This is what we call the polarization. This is what we call depolarization ellipse. So polarization is nothing more than the vector nature of the electromagnetic field. We can have, therefore, many different cases, okay? What happens if our field only moves, okay, only propagates in the horizontal axis? What we have is this, okay? So we have what is called horizontal polarization state. On the opposite, if the field only varies in the vertical direction, we have vertical polarization state. And we can also have a field that describes a line, but tilted. So we have an arbitrary linear polarization state. On the opposite, we can have the field to describe a circumference, okay? Described to the right or clockwise or counterclockwise. In that case, we have left circular and right circular polarization states. So as you can see, we can go from linear to circular. In the middle, we have a full range of elliptical polarization states. Okay, and this is the most important thing. We call polarization to the shape of this polarization ellipse. So this is why we talk or we hear about a linear polarization states, circular polarization states, or elliptical polarization states in the most general case. When dealing with SAR images, and you will see later on, we deal with two types of targets. What we call deterministic scatters. In that case, the polarization of the electromagnetic field scattered by these targets is always constant. So we call about completely polarized wave. So the polarization state of the wave does not change. Okay, but on the other side, when dealing with natural targets, forests, grass areas, crops, etc., we are dealing with what they are called distributed scatters. In that case, the polarization state changes with space and time. So in that way, what we have is partially polarized wave. So we have to distinguish these two cases when dealing with polarization or when dealing with the polarization of a wave. Okay, so we have until now, or we know about what is polarization. Okay, is the state of the electromagnetic field. How do we use that property to get information about the target? Okay, because at the end is that we want to know is to retrieve some information about the target we are looking at. So in here, I put a kind of toy case or academical case. So what we have the separation between two media, okay, which is represented in here, and we transmit this incident wave. What we have is two waves, the transmitted wave that goes into the second media. So we are not interested basically into this wave because it's attenuated, and we have the scattered wave. We are interested into this wave because we will retrieve the information from this wave. What happens? The incident wave is determined by two orthogonal polarization, two orthogonal fields, so therefore it has a given polarization. The target changes the polarization of this incident wave and scatters a second electromagnetic wave with a different polarization. Okay? So what we really want is, what we really make is to compare the polarization of the incident wave. We compare it with the polarization of the scattered wave. And this comparison or this relation is given by this matrix. In this particular case, that you have zeros in the off diagonal. So basically, this matrix, as we will show later on, tell us how the scatter changes the polarization of the incident field to the scattered field. So basically, our goal is to retrieve this matrix and from this matrix to retrieve information from the target. In the most general case, what we have is a full matrix. It's the so-called scattering matrix. And we use to describe then horizontal and vertical polarization states, as I described here. So basically, this matrix is created with transmitting in H, receiving in H, transmitting in B, receiving in H, transmitting in H, receiving in B, and transmitting in B and receiving in B. So therefore, this matrix, and this is the quantity measured by the polarimetric SAR system, tell us how the target changes the polarization. So basically, we want to retrieve information from the fact that the target changes the polarization of our incident wave. And this is very important because this matrix depends, first of all, on the scatter. Depends on the shape of the geometry, depends on the material, depends on the water content, all of them through its electrical properties. So if we are able to measure that matrix, what we would like is to get some information of the target from the elements of this matrix. This matrix depends also on the frequency we are measuring. It's not the same if we are measuring at C-band, as for instance the Sentinel-1 case, that at L-band as the ALOS case, and or the P-band, for instance, the future biomass system. So depending on the frequency, we get different information. Also depends on the geometry. Basically, if you want, depends on the incidence angle. Also depends on the system coordinate, but this is a technical point. And basically, at the end, the most important thing is that all the elements must be acquired at the same time. We cannot measure elements at different times because they are not referring to the same target, especially if the target is moving. How do we measure this scattering matrix? So So this is a classical radar. I would say a classical SAR, if you want. We have a transmitter. The transmitter sends a train of pulses. In this particular case, I have indicated H polarization. This train of pulses reach the target, and the target scatters back this train of pulses also at H polarization that we measure with the receiver. What we can make to start to measure the scattering matrix is to add a second receiver, but this time tuned to the vertical polarization. Okay, so we measure the echoes of the target at the horizontal polarization and the vertical polarization. In that case, for instance, we can measure one column of the scattering matrix. In this particular case, is the HH-BH. Just as a matter of example, I want to indicate that Sentinel-1, the European system, measures one column. In that particular case, is the BB-BH. But in order to measure the complete polarimetric matrix, the scattering matrix, what we need is to give the capability to transmit also in this second polarization, okay, the B polarization. So we make the same process, and therefore, doing this process, we are able to measure the complete scattering matrix. So as you can see, it is impossible to measure the two columns of the scattering matrix at the same time because we are not able to differentiate. For instance, if we are transmitting in H, we are transmitting in B, and the powers are mixed. The problem or the limitation of a polarimetric SAR system is that as we need to transmit at two polarization states, the pulse repetition frequency needs to be doubled, and this produces the reduction of the swath of the system by 1/2. So we are measuring 1/2 of the swath of a single polarization SAR systems. Okay? Here, I show one example, or some examples, if I may, of some canonical targets and how the scattering matrices are. For instance, you have here the scattering matrix of a sphere, which is 1, 1, 0, 0, dihedral corner reflector 1, -1, 0, 0, trihedral corner reflector 1, 1, 0, 0, okay, a short cylinder, a left-handed helix, and a right-handed helix. So these are academical cases. Nevertheless, I want you to give attention to these two, which are really important, as we will see later on. If we had a system measuring only HH, in both cases, we will have one here and one here. So basically, a single polarization SAR system won't be able to differentiate both targets. Nevertheless, if we have a fully polarimetric SAR system, what we have in the dihedral corner reflector is 1, -1. In the trihedral, we have 1, 1. So magically, having more channels, we can differentiate both targets. And here you can see that the scattering matrix is sensitive to the geometry of the target. Basically, we can distinguish these two targets. So this is the most important source of information of polarimetric SAR data. We will be able to differentiate the geometry of the targets. We will be able to differentiate targets through their geometry, their shape, if you allow me to say that. If we go to the matrix, okay, to the ES matrix, this is the full version, this is the propagation vector, the attenuation, this is the absolute scattering matrix. So in order to be able to work with this matrix, we need to remove the absolute phase. And then, as you can observe here, you have 5 different independent parameters. By the way, in the case of SAR system, HV is equal to BH. So these two terms are equal. So we have only this amplitude here, this amplitude here, and this amplitude here, and the two phase difference. Therefore, as you can see, we have a 5-dimensional vector, a 5-dimensional matrix that allows us to differentiate targets because we have 5 different dimensions. So 5 dimensions is more than 1 in the case of one SAR system. So therefore, with a polarimetric SAR system, we are able to have a better differentiation of the targets. Here is perhaps the most important slide of the presentation because basically tells you which is the information content of polarimetric SAR data. If we combine in this way the images, okay, whenever you have HS plus BB very big, very large respect to the other two components, okay, you can tell that you are in front of single bounce scattering. And single bounce scattering is normally associated to flat surfaces, to rough surfaces. If we make the difference, whenever you have this value really large, this corresponds to double bounce, which is great in this kind of situations. Houses, so you have the double bounce, the first bounce in the ground, the second on the facade of the house, and then the echo back. Another point where you can have this value really big is in the double bounce occurring between the surface and the trunks on the forest. Finally, if we take this element here, whenever this element is high, we are in front of multiple scattering or volume scattering. So in that case, we are in front of forest, as you will see later on. But this is the pictorial way of looking at that. So as you can see, with a proper combination of the elements, we are sensitive to the geometry. We can differentiate surface scattering, surfaces, from urban areas and forest, and pure forest. So this is the most important part of the information contained in polarimetric data. We are sensitive to the geometry, to the shape of the targets. Let's go to see some examples. Here I show some images acquired at L1, about 1.2 gigahertz, C1 5 gigahertz, and this corresponds to Madrid, is the capital city of Spain. This is the south part of the city. So these are the images you see with a single polarization. What happens if we make the RGB decomposition or composition, red, green, or we code every channel with a color? What we obtain is this. We are able to give color to the images. Remember, whenever the HH plus BB was large, here is indicated in blue, you have surface scattering. So all these areas you can see here on bluish, they correspond basically to flat surfaces. Whenever the green is large, what you have is volume scattering. Where you can find volume scatters? In forests, on the left, for instance, and on the right, you can see agricultural areas due to the crops. And finally, whenever you have red, you have double bounce. I don't know if you see, but here, for instance, at L1, you have a large red line crossing all the image. This corresponds to a power line. So what we see here is the double bounce between the ground and the power line, because the power line is a large dipole, it's a large cable, it's metallic cable, so the reflection is really, really high. And finally, if you compare both L1, C1, as I mentioned before, whenever the frequency is high, you are more sensitive to the volume. So that's the reason why at C1 here in the middle, you see more rim, because you are more sensitive, you have less penetration onto the volume. Here is a second example. This corresponds to the city of Santiago de Chile, in Chile. Okay, at the same polarization, L1, C1, you can see the center in the middle, and you can see the mountains surrounding the city. What happens if we use polarization? If we use polarization, we can already see the different type of scattering behaviors. On the top of the mountains, with no vegetation, you have basically what you have is surface scattering. In the middle range of the mountains, you have vegetation. That's why you see green, okay? And in the city, you have both green and red. Let's go to the city. As I mentioned before, whenever you have red, you have a double bounce. So you have a perfect double bounce, okay? As you can see in many areas of the city, whenever the houses are really parallel to the track of the satellite. In this case, the track is on the top and goes from left to right. Okay. For the other cases, you see green in the city because you don't have a perfect double bound. You have a not oriented double bound. So that's why you see basically polling. But in here, combining both, you are able to differentiate the urban areas. Here is another example. In this particular case, we are dealing with an urban SAR system. This is the SAR system from our colleagues in Germany, in Oberpfaffenhofen in Munich. And in here, you can see exactly the same. You have the 3 Pauli components. And if we combine them, we can already identify the different types of targets. In green, what we see in the middle is the forest. In this part in here, and in this part in here. In blue, almost you don't see it there. Basically, it's this part in here, more or less blue. It's surface scattering. And finally, what you have in here is the red, which corresponds to some urban areas. And if you see these particular crops in here, why do we see red in these particular cases of crops? Because as you can imagine, crops are really well aligned, are really well planted. So it's very easy. I mean, it's not random. I mean, therefore, it's very easy that you can reach there a double bound scattering mechanism occurring in the crop areas. In the same way as we were dealing with, the wave, whenever we deal with deterministic targets, which basically are urban targets, we basically have a completely polarized scattering. Nevertheless, when dealing with distributed targets, we are dealing with partially polarized scattering. So basically, for those of you who are interested, these particular cases are the most important one. And the fact that we have partially polarized scattering means that we have to deal with the speckle noise component. So for that, in order to cope with this noise component, you have plenty of speckle filters that allow us to reduce this noise component and therefore to estimate information for distributed targets. Okay, what we have until now? First, we have wave polarization. Remember that polarization is nothing more than it's nothing more than the vector nature of electromagnetic fields. First point. Second point, when dealing with scattering, with the transmitted and the received wave, both are related with the scattering matrix. And this is what finally a polarimetric SAR sensor, a polarimetric SAR radar measures, the scattering matrix. And remember, this scattering matrix relates the polarization of the incident wave with the polarization of the transmitted wave. The incidence with the scattered wave. So basically, this matrix contains the information how the target changes the polarization of the wave. So inverting that matrix, we can get some information about the target. So here, I'm going to show some applications now and how this matrix can be used for different purposes. Basically, when dealing with polarimetric applications, what we make is to go from the measurements to our target. Basically, at the end, we don't deal with the target itself. We deal with the physical model, the electromagnetic models of the target. So we have parameters that describe this model that we hope they contain information about our target. Of course, you have to deal with calibration issues, the fact that we need to recover the true measurement made by the system. We have to eliminate any kind of bias. We need to have an estimation step, which basically goes to the part of the speckle. We need to retrieve the observables. That for our case, the observables is the scattering matrix. Is the most important observable. Is this scattering matrix, and therefore from this matrix we need to be able to go to some scattering models and how our target is represented in terms of the scattering matrix, and therefore we can relate our observables with our target. And this is the idea we want to make. So therefore, When dealing with applications, we want to go to this. We want to go from these measurements through this inversion process to the physical model, to the description of our target. Let's go to the applications. First of all, I'm going to show some type of supervised polarimetric classification. Of course, you have plenty of applications. Here, I want just to show the principle and how the availability of polarimetric information can improve the classification. But of course, you can define many classification algorithms, especially those that are now defined in the frame of artificial intelligence or machine learning that can even obtain more information from the data. But the principles at the end are the same. What do we have in a supervised classification? We have the data here. I sample some of the areas, and then what I make is to compare the whole image against these areas. If we make that, we can have these classification results. So you can see, as we have, remember, 5 different independent parameters to characterize the target, we can classify the target. So as you can see, in red, you have most of the forest, okay? And I can tell you this visual classifier is very simple. You can differentiate the runaway and all the pieces of the airport, which are in light blue, different type of fields in green, all the urban area here. So as you can see, you can classify. Of course, the classification is not perfect. In some classes, you obtain a really high rate of classification. Class 1, class 2, for instance, are above 90%. Some other classes are misconfused, 40%, 26%. Okay, but in general, you obtain a very good classification with this confusion, with this supervised classification. As I mentioned before, you can use more advanced techniques for classification in order to reduce this misclassification. Here I have some example provided by Professor Dr. Johnson Lee from the NRL in the US. So in here, we are doing exactly the same for forestry, okay? And what you have here is fields of trees with different ages, okay? Here you have the ground truth. And here you have the information. So basically, the more green you have, the higher are the trees, okay? And whenever you have blue, as for instance in this field, what you have is basically flat areas, okay? And in here is pure blue because this corresponds to water. This is named Flevoland in the Netherlands, in Europe, in North Europe. What happens if we use C-band data? This is the rate of classification we obtained with polarization, about 66%. If we use L1, which is a lower frequency, we have more penetration. Polarimetry gives more sensitivity to the whole canopy, so we can improve our classification that goes to 81%. If we go to P-band, we obtain 71%. This is, for instance, the case that we would obtain with the future biomass system from the European Space Agency. And if we combine them, if we combine polarimetry, remember, with multi-frequency, PLC band, you obtain a rate of classification above 90%, which is extremely good. And this is for forestry. Another application we can make is unsupervised. I mean, we don't tell the classification, the classes. The classes are found automatically by the algorithm. You have, again, you have plenty of unsupervised classification algorithms. This is a kind of very simple based on the entropy and isotropy alpha decomposition theorem. And as you can observe, you can increase the number of classes so you can have better differentiation here. For instance, if you go to the forest in this area here, you can see that different parts of the forest go to different classes. So you have a better capability of discrimination. This is how they compare. For instance, using more parameters. In here, I use 3, H alpha, that are 3 polarimetric the three polarimetric capabilities, parameters, sorry, we are able to differentiate more targets than in the case of using only two. So basically, this goes again in the same direction as I mentioned before. The higher the number, the higher the channels you have, the better classification you have. So that backs the idea that polarization, as it has more channels compared to single polarization SAR, obtains a better classification of the terrain. And these better classifications come from the fact that we are able to discriminate more targets. The final application I want to show is a very important application that is a hot topic today, especially in the frame of Sentinel-1, because we can obtain time series of data, is change detection. We want to detect, we have a temporal series of SAR images, and we want to detect changes between the images. In this particular case, I was working with images in the northern part of Catalonia. Barcelona is in here. This corresponds to the Mediterranean here. And the data correspond to RadarSat-2, this red square here, which is a C-band, is the Canadian system, fully polarimetric, and ALOS pulsar, the Japanese L-band system. And the dates of the acquisition is between 2009 and 2007 and 2000. Here you have the different parameters of the scene. This is how the images look like. As I mentioned before, remember, blue in this particular case means surface scattering. Red means double bounds, so you can already identify the urban areas in the three pictures. And green means volume. And what we want to detect is the changes between these images. Here is the same for the RadarSat-2 with C-band. Okay, remember, blue surface scattering, red double bounds, green volume. So you can already, again, identify the urban areas in here, the forests in the mountains, and some bare areas on the bottom of the images. Here I have detected the changes between the individual polarimetric channels. What I made here is I compare only on the left, the HA channel for the 2007 and the 2009 with ALOS. This is for the BB, and this is for the HB. 0 means big change, 1 means no change. If you compare the three separately, you can see that you cannot detect changes. But if we use the fully polarimetric information, you can already see the big changes that occur in this part. If I compare another set of images, I obtain the same result. As you can see from this result in here, using polarization gives more sensitivity to the changes between the images. And finally, I can compare the changes between the three images. So here is with the HH, this is with the BB, this is with the HB. You can detect changes, but you increase a lot your sensitivity for changes using the fully polarimetric information. In this particular case, this big area of change here, remember, 0 is a big change, here and here, it's a big forest fire that occurred in the area several years before. And therefore, the changes now are due to the changes of the small vegetation you have in this environment area. Also, you can look at the urban areas, okay, at urban. As you can see, some blue spots on the image. In this particular case, we don't have ground truth to indicate which is the origins of these changes, but they are likely to be changes in the urban areas due to the construction of new buildings, of new houses, or the removal of houses, okay? Because these changes occur on the urban areas. If we go to RadarSat-2, it's C-band, we see the same type of behavior. We detect the changes in the individual channels of the matrix, and this is what you obtain if you combine all the polarimetric information. You are more sensitive of the changes, to the changes as you can see here. This corresponds between the the middle of the year in the case of radar SAR2, and these are the changes you obtain. Basically, all the changes here appear in this area, okay, on the top, that corresponds to crops. So basically, you are sensitive to the growing and the harvesting season or the harvesting process of the different crops. Here is the comparison of the 3 images we had in that particular project, and you can see that you see changes everywhere, but most of the changes occur in this area that are due to the harvesting process at the end of the springtime here in the North Hemisphere, okay? Because we are facing, in these dates, we are facing the summer. Here you can see even more the details. This image corresponds to the last image of the series. So you can see that in this area you have blue, okay, that corresponds to bare area. Here, the crops have been harvested. So therefore, you go from the growing season to the harvesting, to the flat surface. Therefore, so you see a big change. And you can also spot, or you can identify other changes, okay, in other areas due to the crops or the urban areas. So as you can see here and everywhere, you are really sensitive to the changes, and you are really sensitive, of course, thanks to the multi-temporal acquisition, and this is very important, but you gain much more sensibility. You are more sensitive to small changes if you use the fully polarimetric information, okay? Because, as I mentioned before, polarimetric information depends on the geometry, and if the geometry of the target changes across time, we are sensitive to those changes of the geometry. In the case of crops, it's very clear. You go from a time where you have the big crops growing to a time where you have no crop because it has been harvested. You go from volume, due to the fact that you have the crop, to the bare surfaces because the area has been harvested. So you are sensitive to these changes, okay? In the case of houses, the geometry has changed completely. You have from single bounds because the area is flat to double bounds due to the new houses, for instance. Or the opposite, if a house has been removed, you go from the double bounds to the single bounds of the house removed. And just before to close this presentation or this lecture, I would like to give you some take-home messages that are really important from this lecture. First of all, as you have seen, SAR systems allow to obtain information of the Earth's surface with a high spatial resolution at the microwave part of the electromagnetic spectrum. And the most important thing is that these data are obtained independently of the weather and the day-night cycles. If we take polarimetry to the SAR systems, we can have, as I mentioned before, high spatial resolution information, but we have information about the geometric properties of the target. Also, you have sensitivity to the electric properties. Also, you are sensitive because you are working with the electromagnetic, with the microwave part of the spectrum, you are sensitive to the dielectric properties of the observed target, okay? And this increase of information is due to the fact that we are increasing the number of channels. From single polarization system to a fully polarimetric SAR system, we are going from 1 channel, 1 amplitude, to 5 channels, 3 amplitudes, 2 phase difference. And finally, we don't have to forget that pulsar imagery interpretation, of course, is different from optical, but it's not better, it's not worse, it's different. In polarimetry, as I mentioned before, you are sensitive to the geometry. With optical, you are sensitive to a different kind of information. You are sensitive essentially to the chemistry of the plant. So both of them are complementary. And this is why nowadays the trends on the use of remote sensing, basically, and how to extract most of the information from our target comes from the fact of combining different sources of information. This is what is called data fusion. If we fuse the polarimetry, for instance, with optical, we are sensitive to both things of the target, to geometry and to the chemistry, as I mentioned before. Okay? So this is the end of my talk. This is what I wanted to give or to present you. So as I said at the beginning, we learned about what's the meaning of polarimetric information or polarimetry. We have seen which is the physical information content of this polarimetric data, geometry. And finally, I have presented some particular applications where polarimetry shows the advantage of or shows improved results with respect to single polarization system. Thank you very much. And now, if you want, I'm open to answer your questions.
Thank you, Professor Carlos, for your very nice presentation. Very didactic and enjoyable to start studying polarimetric SAR data. Now we open the section to questions, and I invite Professor Carlos Cardenas to conduct any question, as well as Aline and the audience that can.
Okay, thanks, Fatima. Good afternoon, all. Thanks to the organization, in special to Beraldo, for the invitation to participate in this summer school. I am very happy for this participation. Of course, thanks a lot, Carlos, for your very interesting and nice talk. Thanks again. Then, first I want to say that we know that the polarimetric system have a lot of application over the grid spectrum. Hope Dr. Lopez showed in you a nice presentation. It's very interesting how the mathematical processing can say us a lot over determinate targets. I think that is very amazing. That is very, very nice. This tool has a great potential. For example, my experience with the polarimetric system is in application over a glacier in Antarctica and Patagonia. We work going to the Carlos in paper, and where it's possible to know the snow or icy composition and the relation with ocean or climate, where the polarimetric theory can help us to global answer, a global question. And this possibility is very, very important. Then, so now my question is, we know that the polarimetric system allows estimating the physical characteristic of a target through the scattering matrix by calculating the values of the matrix. Yeah, scattering matrix.
Yes.
Then, what do you think, Carlos, about the current capability of polarimetric system, and what is their future?
The future, okay. Of course, the future is linked to the availability of data.
Yeah.
And this is very, I mean, this is the key question, okay? And the future is extremely promising. As I mentioned before, you have the European Sentinel-1 system. And it's not fully polarimetric, it's dual pole. I mean, you have only 2 channels, but the most important thing is that you can create time series, and also, it's very important, data are completely free. I mean, any person in any part of the world can download the data. And in that particular case, especially in Europe, they are using this Sentinel system for crop or for agricultural management. And it's very important for agricultural management, and also to shape the European policy for agriculture. This is there. In South America now, you have, for me, which is nowadays the best example of polarimetric system, which is the SAOCOM system, was done by our Argentinian colleagues. They launched the SAOCOM 1A several years ago, a couple of years ago, and several days ago they launched also the SAOCOM 1B. And this is very, very important because it's at L1, and I think it will be extremely useful for forestry applications. I mean, at the end, polarimetry, from my point of view, is the unique tool to explore volume scattering that occurs in crops, okay, that occurs in forest, and as you mentioned, in ice, snow. And this is why it's also important to use polarimetric scattering for glacier studies, as you did in Antarctica. So also we will have the future, our colleagues at NASA, they will launch in 1 or 2 years also the NISAR system, which will have also polarimetric capabilities. We have other systems which are commercial, like the Canadian RCM, Radarsat Constellation Mission, the ALO system from the Japanese, but they are somehow commercial. So the availability of data is less, I mean, you don't have such a big data availability as you may have with Sentinel or with the future NISA system. And just to end up, Europe is also planning to have a future Sentinel system, Sentinel 12, if I remember well, and will be a L1 SAR system, replicating more or less the SAOCOM. And the important thing is that also in that case, data will be for free.
Yeah. And other question, sorry, Fatima. What do you think about the how many data from open source internet for polarimetric processing? Do you know determinate a link or association?
I mean, as I mentioned before, you can go to the internet. You can go to the Copernicus program of Europe. I mean, it's that I remember. I think it's copernicus.eu, and there you can find all the links to access all the Sentinel. I mean, the policy of European Community about remote sensing data is that data are free for everyone. It's free. Sentinel 1, Sentinel 2, Sentinel 3. Nowadays, they will launch Sentinel 6. All data. I mean, the general policy of the European Space Agency is all data for free. That's also nicer from our colleagues at NASA. They will release all the data. You have also the UAV SAR, which is the airborne system in a drone for the colleagues at NASA. Data are all for free. You can check on the internet, and all the data are for free. I mean, this is for me is the most important, and it's the key point to make data free for people to play with.
Nice. We have information also.
Okay, thank you. Aline, can you use the room?
Okay, I have a question based on what you said. You think it's possible to obtain a good result in studies on plantations or forests with only dual polarization from Sentinel that we have available for free?
Can you repeat the question? I didn't hear the question.
Okay. Based on what you said, you think it's possible to obtain a good result in studies on plantations or forests with only dual polarization?
Yeah, you can. I mean, for sure, yes, you can.
From Sentinel.
Yeah.
Yeah.
I mean, the most important thing.
Okay.
No, go ahead, please.
No, that's we have available for free. That's it.
Yeah, I mean, as far as I know, Sentinel 1 operates worldwide with no problem. The only issue that differentiates different areas is the revisit time. I know that in Europe, the revisit time is 6 days. And in some parts of South America, it's about 12 days or about 8 days. It depends on the geometry of the orbits. Okay, on the poles, I mean, it's closer because you have more passes of the satellite. On the equator, it's less stringent. But for instance, I was working in the mission advisory group of the Roselle future Roselle, and they foresee to have a time series of 3 days, a difference of only 3 days, and 1 day on the poles, or less than 1 day, 1 day or less on the poles.
Okay, thank you.
Okay. Professor Carlos, I have one question, and we have another one in the chat. And
okay.
my question is about change detection application. And when you look for changes in polarimetric data, you look for changes. You can look for changes in the coherence matrix distribution. And what kind of similarity measure can we use to compare the similarity of these two scenes from good temporal data? And how can we identify the type of change and the amount of change regarding increase or decrease of this change?
Okay.
How can we approach it?
About the measure of this similarity, for instance, in the example I presented in my presentation, it was the maximum likelihood between the changes. Okay, in that particular case was that. You can also have the concept of distance between matrices. You can have, for instance, some prototypes. I mean, you can measure the change from those prototypes. So these are the concept of distance. Of course, these distances can be based on the geometry of the matrices, on the distribution of the matrices, because this is important. But changes, I mean, you can have many different techniques to the changes. About your second question on decrease or increase of change, I mean, basically, if you analyze the time evolution of the change, of course, you can differentiate between, let's say, a positive change or a negative change. I mean, but in order to have that, of course, the change only has sense if you have a temporal series, okay? So combining both the temporal and the polarimetric information, you can determine if your change is about an increase or a decrease of something. So you can be also sensitive to that type of information. Indeed, there are works where you can classify the change. I mean, you can differentiate different type of changes. This can be done. You can classify the changes if you want.
Okay.
But combining both the polarimetric as well as the temporal information.
Okay. Thank you very much.
You're welcome.
We have another question in the chat. Matthias is asking how much is a large value for that polarimeters?
Okay, this is a very good question. Basically, in order to say that something is large or not compared with the other, what you measure is the relative changes between the components. Okay, you don't really measure the absolute value. You measure the relative change. So basically, you normalize the 3 channels and then you compare them. It's the relative changes.
Okay, and we have time to another question from Rafael Rosa, and he is asking for if you know
he is asking about to identify illegal plantations, camouflage illegal plantations. I mean, I haven't seen a direct work on that, but I can tell that if you have sufficient spatial resolution, because it's a combination of different things, I think you can be able to identify this type of things into the polarimetric data if you have sufficient spatial resolution.
Okay.
Here is another question. Do the changes are calculated by image differentiating or other algorithms? Normally, the changes are obtained by more complex algorithms. For instance, the changes I presented in my presentation were using a kind of maximum likelihood estimation. I mean, I was using the statistics of the data and comparing that, because by simple differentiation, you won't obtain very good results, I would say. You need more advanced techniques, and you in the reference papers that you may find on the internet, you can have many algorithms that go beyond a simple differentiation of images.
I think that this calculus are relied on the model of the data. Of course. We can't do anything without considering the model of the data. So,
and normally, the most important model you have to take into account is the data distribution.
Yes, the data distribution. And Professor Carlos, do you have another question?
Yeah,
we have time.
Okay, I have a note here. The polarization is defined through the electrical field, yeah?
Okay.
Then linear, circle, or elliptical. My question is, what difference there is between a measurement with a different polarization? For example, linear with a circle. Where is the difference?
Where is it? No.
Maybe a lot of information with a circle compared with a linear or other.
I mean, I didn't mention this in the text, but it can be demonstrated that to use full power of the polarization, you only need to measure in two orthogonal polarization states. Set in a different way, if you measure on the horizontal and vertical, which are orthogonal, you can synthesize the response of the target at circular polarization. Indeed, and this is the main advantage of polarimetry, is that measuring at two orthogonal polarization states, you can synthesize the scattering matrix of the target at any polarization state at hand. So this is why you don't see systems operating at SAR systems operating at circular polarization. Full pole systems operating at circular polarization states, because it's not necessary. You only measure in two orthogonal, horizontal and vertical, and therefore you can synthesize any polarization state.
Yeah, then it's easy with linear polarization to calculate, for example.
Yeah. Yeah, you don't need to calculate circle.
Okay, thanks.
You're welcome.
Okay, and to conclude our session of questions and lecture, I would like to know if you have any tip to the young professionals who are dealing with polarimetric SAR data and remote sensing of environment problems, and how can you suggest them to join this knowledge and input their career or something like that? What kind of tips do you have for these young professionals?
The main tip for the young professional, what a question, wow. Important one. I mean, my most important tip for the young people is basically to have fun with the data. I mean, to have fun doing remote sensing. I mean, if you have fun, at the end, you are happy. Polarimetry, I mean, it has potential for the future, okay? Especially because we will have polarimetric systems. And from my point of view, one of the most important directions would be on studies of the vegetation and studies of crops. Why? Because nowadays, if we face climate change, one of the most uncertain elements of that could help us to fight against the climate change is the effect of vegetation. The effect of vegetation is not really well known. It's not really well characterized. And polarimetry offers the possibility to explore vegetation with high spatial resolution. So therefore, I think it may contribute to reduce the uncertainty of this component on the on the fight against the climate change, I would say. I mean, I know this is quite general, but honestly, I believe that if polarimetry may contribute to our big problem of societal problem of climate change, it will go into the direction of vegetation. And this is very important because in a couple of years, the European Space Agency will launch the biomass system, which is a P-band, fully polarimetric SAR sensor, especially focus on forest studies. And again, the data will be for free. So you can take the data, you can make your PhD, you can make your research using that data.
Okay, thank you, Professor Carlos.
You're welcome.
We have more questions. Veraldo,
Okay.
Can you hello, Veraldo. In the chat, we have another one from Murilo Shranda Silva. In your presentation, we saw the benefits of full polarimetric data for change detection in other applications. But most of the SAR data sets still operate at dual polarization. Why?
Why? The answer to that question is that to make it has several answers. The main thing is because technically, to make an antenna, a fully polarimetric antenna, in both in transmission and reception, is really complex. And the second option is that if we use a fully polarimetric system, the size of the images you measure are 1/2 of the images measured with single polarization system. So basically, if you compose all of this, if you put polarimetry, you compromise somehow the revisit time because the size of the swath is smaller than the size of the swath of a single polarization system. So it's a kind of compromise. And nowadays, most of the systems go into the dual pole, I would say. I mean, but in the future, SAOCOM is fully polarimetric. NISAR, it will be fully polarimetric. The future ROSEL will have also some fully polarimetric capabilities. ALOS Pulsar from our Japanese colleagues is also fully polarimetric. You can retrieve data on full polarization. Biomass will be also fully polarimetric. So, I mean, they are half-half.
Okay. There is another question from Juan Douglas. What will be the preconized speckle filtering algorithm for Professor Carlos?
Okay, this is the $1 million question, I would say. Big, yeah, because we have been discussing this question in the community many times, and I remember discussing this question with Professor John Sengley from NRL in the US. At the end, I would say that there is no a perfect speckle filter. Everything will depend on the application you have. Maybe for your application, a very simple filter like the boxcar, which is a simple low-pass filter, you can make it. Or maybe in your application, you need something that goes really into the maintenance of the spatial solution. Therefore, I would recommend you to go into a non-local means, which is a really advanced filter, okay? But I mean, the most honest answer to that question is that the filter you have to use depends on the application board you have behind. You have to test the different filters, the different options with the software packages you have in hand, and then to select the filter that gives you the best results.
Okay. Thank you, Professor Carlos. Aline, can you conduct the other questions that are in the chat, please?
You speak.
We cannot.
You are muted.
Yeah.
We cannot hear you. Vera,
I'm sorry.
No problem.
We have another question from the chat, from Jonathan. He's asking, I understand that the sensor registered a matrix of polarizations and performs an inverse to decompose them. Is this related to the inverse problem of remote sensing?
It has nothing to do with the inverse. It's a complete. This is up to, of course, from the technically they are matrices, but they are two completely different problems. Okay.
Okay, another question. We have time.
Fatima, is possible another question?
Okay. Yes. Yes.
Yeah.
Yes.
Carlos.
After concluding Aline with the chat, we can pass the word.
Okay, this is
just one more. From Rafael Rosa. What are the current applications related to the use of polarimetry to measure dielectric characteristics?
The golden application in that case is soil moisture estimation. I mean, I would say that if I can use these big words, the main applications of polarimetry would be classification and soil moisture estimation. For sure, it goes to that.
Okay, yeah. Professor Carlos, do you have a question?
What is the potential when combining polarimetric data with other SAR modality, for example, interferometry or other multitemporal data? And if there is any type of tools to allow this integration, for example?
Okay, I mean, you can combine everything with everything. Mm-hmm. The only point you have to take into account is that depending on what you combine with what, you will obtain different information, okay? As I mentioned before, as you mentioned, you can combine polarimetry with interferometry. Now, this is a very important application, which is polarimetric SAR interferometry. Remember, with polarimetry, we were sensitive to the double bounce, single bounce, and the volume. With interferometry, you are sensitive to the height, okay? With topography, to the height. So basically, with polarimetric SAR interferometry, you are able to be sensitive to the height of these scattering mechanisms. So if we remember the slide where I presented the physical content information, you would be able to locate the ground, the single bounce on the ground. You will be able to locate the volume on the canopy of the tree. You are sensitive, therefore, to the forest height, and therefore, with some kind of processing, you can be sensitive to the biomass. This is a very important application. And indeed, this is the objective of the biomass mission of the European Space Agency, to map worldwide biomass. Yeah. If you combine with military frequency, you can improve your classification, as I presented here in the lecture. If you combine with time, you can be more sensitive to the dynamics of the target. You can classify better the targets. And what else you may have? I mean, basically these are the combinations. With interferometry, you can locate the scattering components in height. With time, you can have better characterization of your changes. With frequency, you can have a better characterization of the target in terms of classification. So, of course, you can combine everything with everything. As I said, just to finish this answer, you need to really take care of the information you obtain, because in each case, the information is different.
Yeah, then with this combining, become more information, additional information, and volume for this information, or?
Sorry, repeat again.
Become more information with this combining.
Yeah, of course. I mean, but at the end, you have to, as I presented in my first slide, the more channels you have, the more information you have. So the better capability to distinguish or to characterize things.
Yeah, okay.
But this is not all the answer. What I mean is that depending on which combination you are making, you are sensitive to a different physical aspects of your target.
Other physical aspect.
Yeah, you can be sensitive to other. Okay. I mean, with time, you are sensitive to the geometry and with the dynamics. With interferometry, you are sensitive to the geometry and to the height. With the frequency, you see different things. With the geometry, you see different things also. So, I mean, there is no straightforward answer for each combination. You have to look and to see what you see with the combination you have in hand. And at the end, you can combine everything with everything, but you have to be careful what you do with that.
Okay. And tool?
Tools. Okay, I was hoping for this question. I mean, no problem. You have what for me is the most important tool is the Pulsar Pro. It's a software developed by Professor Eric Poitier from France. It's Pulsar Pro. You type, and you get it. I mean, it's sorry?
The combining
it's everything with everything. I mean, it's entry rated. It's the most important thing, because I was working in my postdoc years in France. I was working with that. The most important thing, you have an amazing quantity of tutorials in terms of slides. The code is open. So you can look at the code if you want. You can use the code. I mean, it's all for free, because this is the SAR policy. Everything is free, open. So use it, feel free, go, break the code. I mean, this is for free. You have also the Snap tool, which is the official software from ESA, also open. You have everything in there. You have the connection with Google Maps. You have the connection with all. That for me, I mean, the two software which are open. Of course, you have private, and in there, I don't want to go into that direction. I would like these open sources. You have the Pulsar Pro and the Snap. And of course, you have all the programming languages. You have MATLAB, you have Python, you have C, and you have plenty of toolbox where you can process the images. But for me, if I would start nowadays to make my PhD on polarimetry, I would start with Pulsar Pro, because you have there, you can read the data for any sensor. You have almost everything on polarimetry. All the algorithms that go into the literature are there in that software. I mean, Eric made an amazing job in collecting. All of us, on all the community, were giving the programs to Eric to put them on the Pulsar Pro. So you have everything there for free and open.
Okay, thanks.
You have I think they will release the new version, if I'm not wrong, the next January. That you have go to the current version.
Oh, good. That's a good news.
And especially if you want material to learn about polarimetry, there you have gigabytes of PDF with a lot of information.
Nice. Very nice.
So we have one more question from chat. From Carlos, it's possible to measure the size of the vegetation of Hurricane Iota focusing on the response to help people?
For sure. I mean, think about this. An hurricane provokes changes, damages. So basically, you need to detect those changes, and you can do, if you have the temporal series, you can do that. For instance, when I was working in Luxembourg with my former research group, we were doing something similar. We were analyzing the damages done by the monsoon in the Southeast Asia, which is pretty similar to the hurricanes. And we also detect the floods provoked by the one hurricane in Houston in Texas. For sure, you can detect changes. I mean, if you have the temporal changes, you can detect those changes. No issue. You can do it. And even you can map the extent of the changes.
The next question is from Jonathan. Why are the cross polarizations stronger than the VV and HH polarizations? In the vegetation, always HV and HH have greater contribution than VV and HH. Why?
Okay, this is something technical. In most of the cases, the HV is the largest in the canopies in the forest, but by the following reason: when a wave enters into the canopy, it produces multiple bounces. It bounces in the branches, in the leaves, and everything. And basically, these multiple branches, what it provokes is a change of power from one polarization to the other. So we don't keep power in the same polarization. That's why HH and VV are more attenuated than the HV, because basically these multiple bounces occurring during the canopy provokes that most of the power we transmit in one polarization appears in the other. And that's why HV is normally higher, theoretically higher in volume.
Okay, just one more. In the examples given, you have basically just three categories: this single bounce, double bounce, and volumetric scattering. How do you make further classification into more categories like 7 to 9?
Okay, because that interpretation I gave was a reduced interpretation of the polarimetry. Because in that case, I was using only the amplitudes. I mean, this is the first order, I would say, approximation of the information. If you include, remember, I was showing 3, but we have 5 different parameters. So if we use the intensities plus the phase, you can distinguish more targets. Why we only use these 3? Because when we want to represent them on a screen, we can do this only. We can represent up to 3 channels. We are not able to combine more than 3 channels. This is a simple visual tool, but you have 5 different parameters, so therefore you can distinguish more things, and you can go to 7 or 9. Why we don't have a decomposition over C4 matrix instead of C3?
Aline,
Okay.
Aline, I think that we can conclude with this last question, and then we finish the session.
Okay, HV, I mean, basically, they have seen the HV is different in VH in forest target. Okay, this is a very good question. Theoretically, forest and most natural targets are reflection symmetry targets. That's why HV is equal to VH. It is true that HV may be different to VH, but in most of the cases, these differences are due to the thermal noise of the SAR system, not to the target. And that's why you see different values. And we use C3 only in monostatic system, where your transmitter is placed in the same position as the receiver. If you had a bistatic system where your transmitter and receiver are at different positions, of course you will have a C4, and you have to use C4, because in a bistatic system, HV is different from VH.
Okay, so we have to thank you again for your presentation and answering the questions.
It was a pleasure.
It was a pleasure to be here with Professor Carlos Cárdenas and Aline
You're welcome.
In this meeting, and I close this section. And Beraldo, can you appear? Okay, thank you very much.
He's mute.
It's mute.
Oh, okay. Yeah, I can just click here. Yeah, thank you tremendously for the job, all the members of the share session as well. Carlos, as a distinguished lecturer, thank you tremendously for accepting our invitation, for being here.
The pleasure is mine.
And yeah, we hope to count on you on the forthcoming lectures as well. And
I'm always available.
For coming to Brazil too.
Oh, I would like. Okay, thank you very much.
Yeah,
thank you.
Thank you all. We will finish then these sessions. Please be aware of our next talks, and there will be a quiz in our webpage as well, so you can earn some souvenirs if you fill it correctly. There are some challenges coming. Thank you a lot, and wish you all a nice weekend.
Bye-bye.
Bye-bye. Bye-bye.
Bye-bye.